day, students. Today we shall derive the metrics used to represent the position of an image plane. Let us recall the matrices used to represent translation, refraction, and a system matrix. Translation matrix T was represented as matrix 1, 0, d by mu 1, where d is the distance traveled in the z-axis and mu is the refractive index of the medium. Refraction matrix R was given as 1 minus p 0 1, where p is the power of the refracting surface, mathematically given as mu 2 minus mu 1 by R, where mu1 is the refractive index of the first medium, mu2 is the refractive index of the second medium, and R is the radius of curvature of the refracting surface. System matrix S is given in Gauss constants as matrix B minus A minus D and C, where A is given as P1 plus P2 minus P1 P2 d by mu. B is given as 1 minus P2d by mu. C is given as 1 minus P1d by mu, and D is given as minus capital D by mu. Okay, now let us consider the case where we can trace the image of an object. For that, consider this to be the optical z-axis. On this, we are placing a lens. An object, as shown, is placed in front of the lens O, and the object is called O, O dash. In ray coordinate representation, we choose a point of the object as the source of the rays. So let the tip O dash be the source of the light ray, and light translates through air of refractive index 1 towards the point A. At the point A, light meets the lens, and in the lens it undergoes first refraction, then translation through the lens, and second refraction at the second surface. So this is actually what we derived earlier in the system matrix. So instead of the lens, we can assume the light ray undergoing the operation of a system matrix for lens. And after the lens, again light travels through a straight line in a homogeneous medium of refractive index 1, that is air, to form the image at this point, and the image is defined as I dash. Okay, so the points taken into consideration here is O dash, A, B, and I dash. Let the height of O dash be x1, height of A be x1 dash, height of B be x2 dash, and height of I dash be x2. The distance of the object from the lens is defined as minus d1 using lens convention, and the distance of the image from the lens is defined as d2. Let us define the ray coordinates at O dash, A, B, and I dash. The ray coordinates at O dash is given as lambda 1, x1. At A is given as lambda 1 prime, x1 prime. At B it is given as lambda 2 prime, x2 prime. And at I dash it is given as lambda 2, x2. See, we have defined the coordinates in such a manner that the incident ray remains, the coordinate remains lambda 1 x1, and for the emergent ray, the ray coordinate remains lambda 2 x2. So the terms in between are suitably named as the primes of each of the rays. Okay. Now the first operation that here light undergoes is light from O dash translates to A. So it undergoes translation. Now this can be mathematically represented as the ray at A, lambda 1 prime, x1 prime, to be given as translation matrix operating upon lambda 1 x1. That is 1, 0, minus d1, mu becomes 1 because it is placed in air, and 1 into lambda 1 x1. Let us this be the first equation. Now the second operation that takes place is light travels through the lens from point A to B. That is, light travels through the lens. So the light ray undergoes the system matrix for a lens. Hence, mathematically it can be written as lambda 2 prime x2 prime is given as matrix operating upon, system matrix operating upon lambda 1 prime x1 prime. Okay. Now the matrix form of the system matrix is B minus A minus D C upon lambda 1 prime x1 prime. And let this be the second equation. Now the third operation light undergoes is again from B to I dash, light undergoes translation. Right? So I can mathematically write this as lambda 2 x2 is given as translation vector operating upon lambda 2 prime x2 prime. That is matrix 1, 0, d2, 1 operating upon lambda 2 prime x2 prime. Now this equation can be rewritten as lambda 2 x2 is equal to 1, 0, d2, 1. Now instead of lambda 2 prime x2 prime, I can substitute the second equation as b minus a minus d c upon lambda 1 prime x1 prime, right? Again, substituting for lambda 1 prime x1 prime, I can write this is equal to 1, 0, d2, 1 into b minus a minus d c. Substituting using the first equation for lambda 1 prime x1 prime, I can write 1, 0, minus d1, 1 into lambda 1 x1. Now the product of these three terms can be used to represent an image plane. Let us take the product. I can write the product of the first two terms will be given as b minus a b d2 minus d and minus d2a plus c into 1, 0, minus d1, 1 operating upon lambda 1 x1. Taking the product again, I write b plus a d1 minus a b d2 minus d plus d1 d2 a minus c d1 and c minus a d2 upon the matrix lambda 1 x1. Now the system matrix for the image plane is written as matrix lambda 2 x2 is equal to b plus a d1 minus a d1 d2 plus b d2 minus c d1 minus d c minus a d2 upon lambda 1 x1. Right. Now we need to find the equation for the image plane or a condition for the image plane. For that, we are going to assume that our object is become a point object. Now we replace the object OO dash with a point object. Okay. Now the points, now if the object is a point object, the image also becomes a point image. Okay. The light ray from the point object translates through air, then meets the lens at point A, then the lens operates upon the light and it emerges from point B, again translates through air to the point I dash. Here, the height of the object x1 is 0 and height of the image x2 is again 0. Now from the matrix equation, I can write two equations. Lambda 2 is equal to b plus a d1 lambda 1 minus a into x1 and x2 is equal to, this is a longer term, a d1 d2 plus b d2 minus c d1 minus d into lambda 1 plus c minus a d2 x1, right? Let this be equation A and this be equation B. Now, when the object becomes a point object, x1 is equal to x2 is equal to 0. It implies that equation B becomes 0 is equal to a d1 d2 plus b d2 minus c d1 minus d lambda 1 plus 0. Okay. Hence, the product term must be equal to 0. Here, lambda is the direction, optical direction cosine and cannot be 0. This implies that the term a d1 d2 plus b d2 minus c d1 minus d must be equal to 0. Okay. Now, this is the condition of the image plane, or this is the equation used to represent an image plane in terms of Gauss constants. Okay, fine. Now, using this condition in the system matrix for an image, I can write lambda 2 x2 is equal to b plus a d1 minus a 0 c minus a d2 upon lambda 1 x1. Okay. x2 can be written as c minus A d2 into x1. Okay, let this be equation C. Now we use the earlier approximation of the object being a point object only to find this condition for the image plane. Okay, so normally we have object to have a dimension of x. So x1 is not equal to 0 and x2 is not equal to 0. Okay, so I can write x1 is not equal to 0 and x2 is not equal to 0. Okay, so this equation C becomes valid in all the cases. And if I write x2 by x1, I get C minus A d2. What is x2 by x1? Height of the image divided by height of the object gives the magnification of the system, small m. Okay, fine. Now, by property of the matrices in optics, I can write the determinant of the system matrix for image plane to be equal to 1. Okay, that is determinant B plus AD1 minus A 0 C minus AD2 is equal to 1. It implies B plus AD1 into C minus AD2 is equal to 1. Now we know that C minus AD2 is equal to M B plus AD1 into M is equal to 1, which implies that B plus AD1 is equal to 1 by M, the inverse of magnification. Okay. Now substituting this term for this term in the system matrix of an image plane, I can finally write lambda 2 x2 is equal to, the first term is 1 by M minus A 0 M upon lambda 1 x1. Okay, so this is your equation D, the system matrix for the image plane, where M is the magnification of the system and A is the power of the system or inverse of focal length. Thank you.